So our first talk is by Liam Golub, Science Enabled by Advances in EUV Technologies. It's an invited talk.
Okay. Now just tell me, how do I get this thing to go to the next slide?
You press that one.
And if I want to start a movie, do I have a mouse? Yes, I do.
Yeah.
Okay. All right. Great. Wake up. Hello. I've been asked to speak on this subject. It's a large subject, and I will narrow it down in particular to the development and the present status of coronal imaging and spectroscopy in the EUV. And that involves mainly the development of soft X-ray and EUV reflective coatings. There have been other developments as well: detector technology, fast electronics, better polishing methods for optics. I will concentrate on the multilayer technology, which has led to two lines of work: high-resolution imaging at specific narrow passband wavelengths, because you want to isolate individual spectral lines as much as possible. And that led to a series of missions, at first rocket flights and then satellites, including the most recent one, HI-C, which I'll conclude with. And the other line of work was imaging spectroscopy, which is basically spectroscopy, high-resolution data obtained on the detailed microphysics, but with imaging capability as well. And that line of work, again, started with sounding rockets and has led to various satellite experiments. The origins of this were in EUV lithography, people trying to make the next generation of microchips, where the wavelength, the diffraction limit, limited the size of the structures you could make, so going to shorter wavelengths was the motivation there. And the scientific advance that we've gotten from this line of work really has been a major revision of the way we see coronal dynamics and what we think is the cause. So, a bit of history. This was the first multi-layer EUV image of the corona, taken in a silicon 12 line at 44 angstroms. Marilyn Bruner put a really crude imager on Jim Underwood's rocket. This was a silicon wafer that was deformed into a roughly spherical shape, the way you make a shaving mirror. But it showed that the method works. The first really high-resolution image of order arc seconds was obtained by Art Walker and his group. It's the top left one. That was at 173 angstroms, the iron 9 and 10. And this led to a whole series of rocket flights which showed the multi-thermal character of the corona, and being able to isolate these individual lines showed you the different appearances of the corona at the different wavelengths. So really, we learned that if you want to even see the whole corona, you have to take into account the temperature dimension as well. And I'll show you that in a minute. Meanwhile, we showed with this rocket flight, when there was a total eclipse going on over Hawaii, over White Sands, the moon was just approaching the sun at the time, and we were able to get an image with the shadow of the moon, with the limb of the moon occulting the corona, and then you could see the drop. Are you able to see that? Yeah. So this is the edge of the moon. This dotted line shows what the scattering, the stray light from a single surface, would have looked like. The multi-layer actually has reduced scattering compared to a single surface. This was controversial at the time. But what it means is when you have a bright source in one of these images, it looks totally unspectacular because there is so little scattering. So that was very good news. This technology also, because you could work at normal incidence, allowed greatly improved imaging spectroscopy. This is the Eunice sounding rocket, which led to the ICE instrument on Hino Day. And I'll show you in a minute how it works. But for instance, you see here the helium-304 line, and you can easily resolve the nearby silicon line, which is only a few tenths of an angstrom away. So you get very high-quality spectra with this kind of instrument. And this is a diagram of what the ICE instrument looks like. So basically the way it works is the light comes in, you have a focusing optic with a coating on it that reflects in the EUV. You focus onto a slit. The light coming through that slit is then re-imaged with a dispersive element onto a CCD. In this case, there are two channels, a long wavelength and a short wavelength one. And you see the corona by rastering, for instance, if you want to do that. You can see the different corona, iron 8 up to iron 16 in this image. And that's the multi-thermal character I was talking about. So the context for all of this work is not just the solar work, but it turns out that magnetic fields appear everywhere in astrophysics. Here's a partial listing of the various places where, whether you like it or not, you have to take into account that you've got a hot magnetized plasma. And the solar case is one of the only places where we can really rigorously test our theories, and that forms actually the foundation for most of the modeling that's done in all these other areas. So the big change we've had when I first entered this field, the view was that you had magnetic loops, confined plasma inside of loops. They would emerge from inside the sun, and the solar atmosphere then consisted of these relatively isolated mini-atmospheres. That view ran into problems when we launched the TRACE satellite, which was the first really high-resolution EUV imager. The EIT on SOHO was up earlier. This had a factor of 5 higher resolution. And what you saw was that the loops disappeared. Those aren't loops anymore. And it turned out that a whole line of theoretical work that had been going on before that, before this was launched, turned out to be relevant. And it became clear that the magnetic topology, the skeletal structure of the three-dimensional atmosphere was crucial. And in particular, the structures we see tend to form at these places where you have quasi-separatrix layers, places where there's a mapping from a very small confined region of field to a very large extended region. That's a whole other talk, but that was the basic change that has come about, not just low in the atmosphere where you have active regions, but we now think further out as well, and in particular, possibly helping us explain how the corona transitions from closed to open. And this is an exciting new area that we can now explore with the modeling and with the observations. And I'm hoping that we can make a lot of progress in that area in what I think of as the transition corona. That was not a UFO, that was Venus. Okay, so where do we stand with all of this? We have 3 outstanding problems, and these problems continue to hang around. We're making progress on what causes coronal dynamics. We do think that we're beginning to understand that topic. We're not fully there yet, but we're getting there. The heating of the corona has been a problem for more than 70 years now. It still is a problem. The high-C rocket, I think, will contribute in a major way. I'll show you a little bit of that in a minute, to answering those questions. And then we have this exciting new question of how we go from a low beta atmosphere back to a high beta, which is the inverse of what happens coming up from the surface. So this high-C rocket is the culmination, in my view, of the imaging work that's been done since the 1980s, the early 80s. This is a picture of the primary mirror from the high-C, which looks just like an ordinary Ritchie-Chrétien telescope. The difference is that it's got a coating on it that reflects the EUV. This is the curve, the reflectance curve, that's wavelength below. So that's 193 angstroms is where it's designed to work. That's the iron 12 line, 1.5 million degrees. And those are measurements made at various places on the surface. So we've got very high quality coatings. And what we're finding, for instance, this is one example, this is a very, very small field of view here. These structures are just a few tenths of an arc second, and it looks as if you've got threads, hot threads. These are 1.5 million degree lines that come together and braid around each other. This, as far as I know, has never been observed before at coronal temperatures. And even during the flight, just a few minutes of data, they seem to simplify. So that bit of observation was in between those dotted lines. The rocket is only up for a few minutes. We have more extensive observations from the SDO satellite, but not this level of resolution. I'll just quickly, I think I have time, show you the movie. And I'll try to stop it. Okay, so there's that frame that I showed you. That is a processed image, unsharp mask, high-pass filter. And you can see flows and simplifications of the field. Okay, do it one more time. So that's the sort of observations we are now able to make. One last thing. There has been a line of work in which the substructure within what you think of as a loop becomes unstable when a current sheet develops as a way to release the stored energy, and it then very quickly fragments. And here, I think, is such a structure. This, again, is only a few arc seconds across, so in other coarser telescopes, this would look like a single loop. But within a time span of only a few minutes, we go from just simple structures to what looks like an outbreak of numerous little threads, which looks to me a lot like these models. So once again, the theorists apparently have, with their crazy theories, seem to have been telling us things that we actually do see. So we're working on this now. I am quite excited about this possibility as well. That would be another view of coronal dynamics. And just the last thing I'd like to say, the high-C data will be made available publicly to anyone who wants it, aiming to get it out next month with analysis software. And Jonathan Certain, who's the PI, will be telling people how to get it when it's ready. Thank you.
Probably have time for one question. If not, I'll ask a question. Where do you said the high-C kind of is the state of the art for these extreme ultraviolet imaging? Where do you see what would be the next iteration on that, on this technology to make the next advancements? Where do you see that going?
Okay. What I just showed you was about 4 or 5 minutes of observing during a rocket flight. That's about as much as you can get. The frustrating thing is we don't know how these structures got that way. We don't know what happens next. And there are dynamics that take a lot longer than a few minutes. So clearly what's needed is to put this up on a satellite where you can get the extensive observation and the kind of sample size that you need with all the various things happening. So that's what I'd like to see next.
All right. All right. Well, thank you. Thank you very much, Liam. Yes, so there, we sparked a question.
How big a year do you think you could make with this kind of coding and still maintain the 2/10 resolution?
That's a good question. This mirror was 22 centimeters in diameter. We could easily go to 35 centimeters with existing facilities. By expanding some facilities, which doesn't take too much, just means a bigger chamber, we could go to 50 centimeters. Beyond that, it gets difficult, but not impossible.
Okay. Thank you. All right. The next talk in these in the session on new innovation, new technologies that will enable us to make our steps forward. We have Mike Gruntman, who's going to be speaking on energetic neutral atom imaging. The next step. Mike.
Thank you. So I can. So let me try. Oh, there's no way to start the pointer, right? Okay, I will just go without that. Okay, so the NA imaging, the next step. So I will start briefly describing energetic neutral atoms and the instrumentation that enabled to get where we are today, and then what happened in terms of experiments and science discoveries. And after that, I will focus on the challenges to improving the instrumentation that will bring the next step in advancing science. So the NA imaging, as you know, it's relatively recent development in space physics, and it has tremendous successes already and made major discoveries. What has been done so far was based on the instrumentation development done in 1970s, 80s, and early 1990s. So the next step in science advancement would depend how we advance instrumentation further. So briefly, energetic neutral atoms are produced in charge exchange collisions. So when an energetic ion collides with the neutral atom and the charge exchange occurs, and if your energetic ions gyrate around the magnetic field lines when charge exchange occurs, neutral atom preserves the velocity of the ion, and the stone from a slingshot flies across the magnetic lines. So you can remotely probe, image, study the populations of energetic ions. So in some sense, it is similar to passive corpuscular diagnostics of fusion plasmas pursued since 1960s. Most common species in space, it's obviously hydrogen protons and hydrogen atoms, but also other species are involved. And ENA imaging so far focused on studies of planetary magnetospheres on the heliospheric interface, and also the tenuous neutral environments around planets like Mars and Venus were also probed. Now, the energetic neutral atom fluxes that are detected are essentially the integrals along the line of sight over the ion distributions in neutral atom densities. So the road to direct detection of ENAs was very difficult. It's actually the first time they were detected 60 years ago optically. And there were enormous difficulties to detect neutral atoms, and the key is that you have to extract an extremely weak signal from the very strong background, several orders of magnitude. And also the fluxes are so small, you need a very large geometric factors of instruments to accumulate enough counts during the mission even. So what a few brave people started to develop instrumentation. It began with a group at TRW, now part of Northrop Grumman, in 1960s in Los Angeles. So, and since the very beginning, the work in ANAs was concentrating on building basic foundations for the instrumentation, but also what happened, very important, in the 1980s, was the serendipitous discovery of ENAs in space, where the instruments that were supposed to measure energetic ions identified certain counts as coming from the energetic neutral atoms in the Earth's magnetosphere and also in the magnetospheres of Jupiter and Saturn by Voyager. So that was IMP 78, IC, and SF-SA81. And actually the term ENA imaging was coined in 1984 by Hank Voss and Ed Roloff in different perspectives in 1984. In 1987, ENAs got to the cover of the GEORAL, sort of showing the first time the potential of the technique. So what are the instrumentation that enabled this development? Well, first of all, there's ultra-thin carbon foils shown here. It's basically 10 to 20 layers, atomic layers of carbon freestanding. They're actually supported by high transparency metal grids. And these carbon foils are used for two purposes. One purpose is to strip ENAs. That means incoming ENAs loses electron passing through such a foil and becomes an ion, and then you analyze this ion and separate it from the background, the UV radiation. The second is using electrons knocked out from the foils by passage of these neutral atoms, and they're using them for time-of-flight techniques. Another technique that was developed is diffraction filtering. Basically, if you have a holes small enough, say comparable to the wavelengths in EUV, then the photons that create all this noise cannot go through, but ENAs do go through. And the third technique is conversion of incoming neutral atoms into negative ions on surfaces. So it's a very comprehensive review with 500 plus references was published in 1997 in the Review of Scientific Instruments. So in 1990s, we finally got the era of ENAs. First major dedicated NASA missions put ENA imaging really in the forefront of research. So the Cassini had an instrument, Inca, that measured ENAs at the Saturn magnetosphere. Then NASA image mission carried 3 instruments that covered ENA fluxes, obtained ENA images in energy ranges from a few electron volts up to a few hundred kilo electron volts. And twins tried to do the first attempt in stereoscopic imaging of the magnetospheres. Now, the smaller missions also contributed importantly, and a number of countries actually got involved. It was Astrid, Mars Express, Mars Venus, SAC-B, Double Star, Chandrayaan. And also now ENAs are being introduced on microsatellite and even CubeSat platforms. In a second, I will say more. In the heliospheric physics, it was Interstellar Boundary Explorer, IBEX, that measured got maps in ENAs of the galactic boundary of the solar system and actually discovered the ribbon. And at the same time, Cassini's Inca discovered ENA belt at slightly higher energies. So these are two things that really challenge our concepts of interaction of the solar wind with the interstellar medium. And also another serendipitous discovery happened in 2006 when Stereo detected ENAs at very high energies from 1 to 15 mega electron volts coming from a solar eruptive event at the surface of the sun. So what were the science advances so far? And the energies of ENAs that contributed are on the right. So in the magnetospheres, it was revealing global configuration and dynamics of magnetospheric storms, asymmetry of the ring current, for example. Lower altitude ENA emission hotspots were discovered at the mirroring points. And also planetary magnetospheres at Saturn were studied. In the heliosphere and the local interstellar medium, the discovery of the ribbon and the belt in ENAs challenged our current concepts of interaction, and we still don't have the clear answers what it is and how it works. Also, there was a new window to the properties of the interstellar medium surrounding the solar system, in particular the velocity vector of the interstellar medium. Then the solar eruptive events, this is a new thing, just recently happened. It may provide a new window to the production of solar energetic particles in flares and in coronal mass ejections. Also, the first ENAs were detected when the solar wind ions reflect from the surface of the moon as neutrals. So what are the challenges to the new missions based on the lessons learned. First lesson is that no unanticipated major problems or obstacles emerged from the space experiments. So they were sort of envisioned. The main challenge remains. It's extremely low intensity of ANA fluxes, which requires very large geometric factors of instruments, which is a major challenge to miniaturizing instrumentation and put on the smaller satellites. And it also calls for effective suppression of any kind of background and noise. There's another challenge for ANA imaging, and which is actually a generic challenge for all imaging experiments when you try to image a very complex three-dimensional object on a two-dimensional image plane. So here improved statistics can help. Stereoscopic imaging obviously should help, and combination with in situ measurements is helpful, and this is something that on the magnetosphere has been tried using data from in situ data from Themis and DSMP, and in the heliosphere Voyager provides some data in the heliospheric interface, and the interstellar probe in the future could provide similar information. So where are the required advances? It's an improved angular resolution, improved energy range, extending energy range to the high energies, and better suppression of noise. Now, speaking about angular resolution, there's a very important to note is that all instruments fall into two categories. One category is a so-called single pixel instrument with a very large geometrical factor but pointed in one direction. Then you have to, using your spacecraft, to scan the sky to obtain the images of the required in the required direction. The second category are the instruments with intrinsically wide field of use, but with the capabilities to extract the directional information of incoming ENAs within this large field of view. Now, this latter kind of instruments has a fundamental limitations because thin foils, or sometimes films, that are sitting in the front of these instruments, they create straggling, that means spreading energies of the incoming particles, and scattering. And this places the fundamental restrictions for an improvement of energy resolution using this approach. So another major topic is suppression of the background due to plasma and energetic particle environment. And again, because fluxes are so small, it is essential basically to kill any and all possible sources of noise. Now, what emerged that collimators and deflectors that are used to remove ions are very complex. Extreme ultraviolet coming from all directions in space and some energetic electrons that may leak inside the collimator may ionize, outgassing atoms and molecules inside the collimator, creating ions that may get inside the instrument, and they are indistinguishable from energetic neutral atoms. So suppression of this kind of source became a major issue. Now also development of the dedicated deflectors for the ENA instruments with energies higher than 100 kiloelectron volts and maybe mega electron volts is a major challenge, and I'm not sure that it is known how to proceed in this direction. In the low energy ENA, say below 1000 eV, there's a lot of work needs to be done to improve the understanding of the physics that is involved in this surface conversion of the particles. And also there's a challenge of producing calibration facilities. Production of neutral particle beams with the energies below, say, 1000 or 2000 kiloelectron volt is a major challenge. So on the mission and the spacecraft level, there are other challenges. Now, some missions obtaining full sky maps rely on the spinning spacecraft, and such spacecraft do produce full sky maps, but the duty factor or dwell time in different areas of the sky varies 1 or 2 orders of magnitude, which is a major disadvantage. Now, libration points, L1 and L2, sun-Earth libration points are important to investigate. In the magnetosphere imaging, we have Earth-Moon libration points that could be very advantageous, putting a spacecraft looking at the Earth and just a magnetosphere environment and studying that. Now, knowledge of the exosphere is also very important. Now, exosphere is three-dimensional. It varies in time, and we have to know it much better, and this remains main just challenge. Now, another thing, putting ENA instruments on the small spacecraft allows to have multi-point measurements, like I say, constellation of CubeSats. In the first example, it's on the Berkeley is flying, UC Berkeley is flying with the Carrier, this instrument on a CubeSat, but having such instruments is very difficult, and it's a new area how to optimize constellation and instruments. And finally, to get to what we can expect. So in the magnetospheres, we need to put angular resolution better 1%, in heliospheres 1 degree, in the heliosphere maybe 1 or 2 degrees. In the sun eruptive events extend energy range, which actually may open a way for advanced warning capabilities for human spaceflight beyond LEO. It's very important. And all other techniques can be used to study interaction of the solar wind with the open non-magnetic celestial bodies and planetary exospheres. So finally, unanswered science question call for advancing instrument capabilities. New instrument physics and techniques do answer science questions, but they bring even more questions. In addition to answering existing questions, history repeats, and I'm sure that the next generation of winning experiments will lead to answers and to new challenges. Thank you.
Thank you very much, Mike. One quick question, and I'll invite Lars to come on up here as we get that question on board. All right. Thank you very much. Excellent. You did such a great job. Nobody had any questions. Okay. The next speaker is Lars Druid. He's going to talk about GEOScan facility from space. A GeoScience facility from space. Excuse me.
All right, well, thank you. I want to thank the organizers for inviting me to this session. So this is a session about innovation and heliophysics. So I have to apologize because I'm going to talk a little bit about earth science, but there's a good reason for that, because I think some of the best innovation we can do is us as heliophysicists cooperating with earth scientists on where we have shared instrumentation and observation requirements so we can all do more. All right, so what's GEOScan? GEOScan is a grassroots scientific effort to create a constellation. It's focused on getting constellations of measurements wherever they're needed throughout the geosciences. And we're focused on, we think this is affordable for the very first time in at least modern history, thanks to innovation in hosted payloads and CubeSats and small sats. And it really began as an effort to pursue Iridium NEXT, to get geoscience instruments on every single Iridium NEXT satellite. And that kicked off with the March 2011 workshop where there's over 120 scientists in both Earth and space science that came together to talk about their sensor ideas and their science ideas on what you could accomplish with constellations of measurements. And the ideas were really outstanding, and that's what I'm going to talk a little bit about for the rest of the day. All right, so why GEOScan? Why do Earth and space scientists want to cooperate together to get common suites of instruments? Well, I'm going to talk about there's a certain number of really, I think, urgent science questions that are never going to be answered unless we get global, persistent observations, and that's only enabled by constellations and satellites. But I think there's a real opportunity to get into a paradigm shift away from very focused satellites, single satellite missions, and to more of a community paradigm, much the way ground-based telescopes operate, where large groups of disciplined scientists get together to decide on a common set of instrumentation that if we put these instruments together, we're going to make great progress in scientific areas, much greater than if we just had one of these instruments all by itself. So I think there's a real opportunity for a change in the way we view and plan for satellite missions. And hopefully you'll share that opinion with me by the time I'm done. But the second kind of main point is this whole idea of if we're going to do constellations, it also gives us a second opportunity to get together and provide common sets of instruments that we can almost effectively mass produce to drive down costs. And so there's a number of these factors that are coming together to, I think, really change the way we can start planning and envisioning missions. All right, so take a step back. Why do we put sensors in space? So these two pictures actually have something in common. They were taken by the very same camera, a large format Hasselblad camera. Now, while this cat is incredibly adorable, it's just a cute picture of a cat. This other picture is the 1972 blue marble picture taken by the Apollo astronauts, and it's said to be the single most viewed picture on Earth ever taken. And so just getting out into space and making a measurement can have an incredibly powerful impound impact, not just on science, but on society as well. But this picture was taken, this is 40 years ago now, right? So this is an outstanding, beautiful picture of the entire full disk of the Earth. And to be honest with you, there actually haven't been that many full disk pictures taken of the Earth since then, just a handful. But still, 40 years ago, what's the modern version of this blue marble? And to me, it's basically Google Earth Live, being able to view the Earth everywhere, all the time, anywhere you wanted to. I think that's this next generation concept of this blue marble picture. It's something that we can definitely do, and it turns out that wouldn't be great just for Google Earth Live, so we can spy on our neighbors, see whether our car's parked somewhere. But it's the same capability that many Earth and space scientists have been demanding and need to solve urgent and long-standing scientific questions. So that's what I'm going to spend the rest of the time talking about. So all the science topics I'm going to be talking about for the next 10 minutes rely on a capability to make measurements everywhere, all the time. So they're typically global science questions, but they're science questions that we can also answer from this common suite of instrumentation. So just to give a quick overview, let me grab the laser pointer here. If we can get, say, for example, GPS measurements in space, we can tomographically image the plasmasphere and the ionosphere. And those same GPS instruments, we heard a great talk in our session earlier this morning, how those same GPS instruments, low-cost, commercial off-the-shelf GPS receivers, not only image the Earth's plasma environment, but it's precisely the raw data that, geodesists need to do GRACE-like gravity imaging. I'll show you some examples of that. Climate change. We've never actually measured Earth's radiation balance. Climate change is thought to result from a less than 1% imbalance between energy coming in, energy going out. We've never tried to measure before because measuring it takes about 30 satellites, at least in space, at the same time. It wasn't a problem we could attack before. I think it's almost a scientific and political imperative that now that we know we can affordably do it, I think we have to do it. And the last important topic is the global carbon cycle, intimately attached with climate change. There's been a long-standing, basically large error bar in the global carbon cycle resulting from we really do not understand how the biosphere has managed to take up more carbon, even as humans are putting more and more carbon in the atmosphere. The biosphere has been keeping up partially with us. And that uncertainty is largely coming from biomass on land. And we all know, many of you, if you forget to water your plants while you're gone for this week, there's dramatic changes within a week. And so you need persistent global observation to understand how land-based vegetation takes up carbon. And we can now do that with constellations of satellites. We can close these decades-long standing problems. All right, so I'll get in a little bit more detail with each one. All right, so this is a climate change aspect. With wide field of view radiometers, these are now can be we think mass produced at relatively low cost. This is simple instrumentation that dates back to the Irby days in the late 60s. But look at this chart up here. This motivates the problem. The top two columns, this is, satellites, observations of albedo together with models. And so this gray bar here represents a change in albedo consistent with a doubling of the carbon dioxide output. And so what's most troubling about this figure is you see that neither even the two satellite systems that we've launched and overlap, their absolute estimates of what the albedo is, none of them agree with any of the simulations. Now, they're stacked to demonstrate how different they are. But look at this. This is politically, this gray bar is what we've been, as a society, been arguing about for decades. And we've never been able to measure this to the level of accuracy required to truly understand what's going on. We can do this now, and I think we have to. One of the reasons why we haven't done it is, we heard a great talk this morning by Warren Wiscombe, you need global coverage. Walk outside, look up. We all know inherently how variable clouds are, for example. If we're not measuring the entire Earth all the time, we're not going to get down to these very less than 1% measurements of albedo. It's not going to happen. We've never had a measurement system. Here's our current system. That's the kind of coverage the current system achieves in an hour. So everything that's happening everywhere else is unobserved. So we're never going to reach that level of accuracy that's demanded to truly provide a next-generation measurement. All right, CO2. This is a great quote. I encourage you guys to look over it. I'm not going to bore everyone with reading out loud, but it drives home, I think, a critical point. Again, it's the same issue with the Earth radiation imbalance problem. Land-based vegetation is so incredibly time variable, and it's not just a function of you have to make observations every day or every week, but you have to make them at a broad range of local times, because the amount of if you just make an observation of vegetation at, say, 10 a.m. any morning. Anyone who's ever watched a sunflower knows that plants change as a function of day. So you've got to make, if we're going to get down and solve these detailed problems, we have to make continuous observations. All right, so geodesy, and I think this is one of the ones that's most exciting because just with, again, with simple, cheap a simple, cheap instrument, a commercial, off-the-shelf GPS receiver, we can revolutionize what heliophysicists want. I personally want to tomographically image the Earth's entire plasma environment, just watch movies of it all the time. Most of our global reconfigurations of the plasma environment, I think we can understand at that next level by just simply watching movies at a high enough spatial and temporal resolution. But precisely that same capability, simple, low-cost GPS receivers on as many satellites as we can get them on, provides the same kind of groundbreaking capability for the geodesy folks. So I think we've all seen how phenomenal GRACE has been, not just for that community, but I think we've all read it on EOS articles and various covers of science magazines. This is an example of some of these really kind of outstanding and I think very future type of observations, being able to see that the amount of groundwater in the Indian subcontinent has been going down at pretty dramatic rates thanks to irrigation over the course of the last 10 years. That's an amazing measurement. It's like the first 1972 blue marble picture of the Earth. It changes, the space-based measurement changes the way we view what we can measure. But the problem with GRACE is, and that's kind of shown by these plots, because it's a single satellite pair, it's like any Nyquist problem. GRACE is capable of basically producing one of these gravity images every 30 days. But these gravity changes that occur over the course of every 30 days, or even long-term, are built together based upon a bunch of much shorter-term changes. Every time water moves around in the atmosphere and in the ground, that's what's causing these long-term changes. And obviously, we have atmospheric water flows that are happening on pretty high dynamics. And so these are simulations of what just precise orbit determination, 3-centimeter accuracy, which is precisely what we're doing on Cosmic, and CHAMP right now. If we could, with a system like Iridium NEXT, have 66 satellites with just GPS receivers doing precise orbit determination to the 2-3-centimeter accuracy level, so no big technological advance, but we just need lots of measurements. If we can do that, that's showing us what we can now get, this high time variable gravity. So we know that gravity varies at a high time rate, never measured it, but we know it's caused by water moving around through both the atmosphere, ocean, and in the land, but we've never measured it before. And just as dramatic and exciting, I think, those groundwater observations of long-term change to India, being able to measure how snowpack in Greenland is forming over the course of a daily process. So this is GRACE gives us a static map. 66 just GPS receivers give us that kind of that time variable, that daily gravity solution. I think is going to allow us to make next generation kind of hydrology observations. And again, it's using the exact same piece of equipment us helioscientists want, GPS receivers, providing a well-known observation. So here again, this is actual data from Cosmic. This is a tomographic inversion of the plasmasphere. And so what I want you to take away from this image is, so the technique works. We can image the plasmasphere. But while this looks pretty good, it does look a little bit like the plasmasphere because there's only 6 cosmic satellites. The tomographic inversion is so coarse, this is not going to teach us anything new about the plasmasphere, simply demonstrate that the technique works. But if we improve this resolution by a factor of 10, now we're going to have persistent observations in 3 dimensions of the Earth's plasmasphere. And that exact same capability on enough low Earth orbiting satellites allows us to do the same thing with the ionosphere as well. So this is a simulation. So this is for the 2003 Halloween storm. We're treating time GCM solution as the truth. This is the climatological model, what IRI says is happening this day, which obviously is not what was happening in the storm. The next one down is a simulation of what our current cosmic and ground-based system would give us. It's approximately close to what was simulated as truth, but it's filled with artifacts, and it's not a scientific type of image. With 66 radio occultation, again, commercial, low cost, off the shelf, 66 radio occultation receivers, we would be imaging, for the first time, about every 10 minutes, the entire Earth's ionosphere at about the degree resolution, latitude and longitude. So every 10 minutes, we get a new one of these images. The accuracy on this simulation showed that there was no location on Earth, no 1 degree by 1 degree location that had an error that was worse than 3 TEC units. All right, so this, again, something that's important in heliophysics. Again, low-cost instrumentation on enough satellites can change the way we do business. And so one of the additional instruments that we'd like to get on are dosimeters. This is an example of a 2-channel dosimeter. That's an aerospace design. And this movie here gives you a flavor for what it would be like to be able to observe the energetic particles in a 2D image fashion. This is actual iridium data right now, but these are memory upsets. These are memory upsets coming down during what was probably the largest solar energetic particle event in the last decade. But what it does is it starts to get, you see the South Atlantic anomaly here and penetration at high and low latitudes. But you see a very dynamic picture of what's going on. And it's the kind of measurements we would like to get persistently all the time. If we really want to understand what's going on with the radiation belts, looking at longitudinal variation and temporal changes of the inner and outer belts, you need a lot of measurements. You can't get around it. We actually don't know right now what the longitudinal variability is and actual temporal variability of losses to the radiation belts, because we've never had a measurement system that maxed out. We've never had overkill on radiation belt measurement system, and it would be nice to know what it is. So all these science are made possible by a collection of comparatively low-cost instrumentation, but put on enough satellites. And I'm running out of time, so I'm not going to get into each details. But let me just jump ahead. Please like us on Facebook to help join with us and see how we can make this happen. And I'll leave my closing thought up there. Thanks.
Thank you, Lars. A quick question on the value of multi-point observations. So we know we've got several missions ongoing or getting ready to go up, and some that are there, and so and as well as the decadal survey had some notional missions that had a lot of multis. So it looks like this is a direction. Yeah, excellent. Thank you very much. All right, our next talk is is given by Charles Swinson. And this talk was actually a very nice intro to that, since it talked about small payloads. So Charles is going to talk to us about solar and space physics science enabled by Pico and Nano satellites.
Thank you. Lars, thank you for the setup too. Very much this has to do with multi-point measurements in the space environment. A few years ago, 2005, I gave a very similar talk. And the motivation was we need to develop the technology for small satellites, because it's the only way that we're going to be able to do these multi-point measurements unless we get a ride on iridium. So what are Pico and Nano satellites? And I blame Sir Martin Sweeting for the non-metric use of these prefixes here for the size of satellites, but they have been enshrined more or less in the lingo of the small satellite community. And I also blame Bob Twiggs for the use of U instead of liter for the size of a CubeSat, because a single CubeSat is a 1 liter volume, but we use the terminology U. So 1 U satellites, 1.5 U satellites, 3 U's, etc. What's been happening here since the first generation of CubeSats is that we're starting to develop standards here for larger containerized deployment of small spacecraft as secondary payloads. So you'll see 6U, 12U, and 27U types of containers that people are talking about. And these are really quite a reality. The launch community is accepting these. As we move on here, I've been involved with the Small Satellite Conference for a long time. This has been kind of a focal point for the development of these small satellites. It's in its 27th years. And the thing that we've noticed here is this is a small satellite conference, so it's bigger and smaller and not just CubeSat. But in the last few years, there's been so much innovation and development and excitement in the community over small containerized deployment of spacecraft that the paper pressure into this conference is actually moving us a bit away from the larger spacecraft, something that we don't want to have happen, but it's the natural reality of getting a lot of people excited about this. We have programs that are sponsored by the military. We have a number of NASA programs, including the Alana program, which is providing a lot of access to space for CubeSats. Back in 2005, when I gave a similar talk, my cry was, we just don't have access to space. We can't get people to put secondary payloads on U.S. rockets. That's completely different now. This is really an opportunity. It's an opportunity for space science. It's an opportunity for our community. It's also something that has been brought together by a team of individuals, people interested engineers, people in government, people in industry that have brought together this possibility of very small containerized spacecraft. So now if we look at the decadal survey, this is out. We have a number of science questions for the decadal survey, some to do with the activity of the sun, the ionosphere, thermosphere, mesosphere, and how energy gets from the sun through this region. We also have the heliosphere, and then we have basic fundamental processes also that are kind of goals for this next decade. We also have been given an initiative called DRIVE, and I'll point out in particular that the first letter D, part of this diversify part of the DRIVE initiative that's proposed in the decadal survey, includes microsatellites. If we look at some of the the priorities here that have been put out, the DRIVE initiative shows up as one of the higher initiatives that has been put forth in the decadal survey, and to develop small satellites, and mainly because we understand as a community, I think broadly, as scientists, that we need the multi-point measurements, that we're in a data-starved kind of situation, and we really need this in order to advance the science. We have a number of reference missions, and I'm going to look at a couple of these. You can kind of see the start dates here for some of these. As we focus, there's a lot in the decadal survey, and as I think about how small satellites can be used to accomplish decadal survey science, it became too large for this talk, and so I'm focusing mostly here on the atmosphere, ionosphere, magnetosphere region here. And these are the science questions that have been pulled out for this community. And as I point out, there's this study here from TEC measurements over Japan and airglow measurements over Japan. These are 2-degree kinds of structures that we are seeing. And this begins to give us some idea of perhaps the type of resolution that we want to get down to address these kinds of questions. It's certainly sub-degree kinds of measurements. One of the reference missions that's been proposed is the Global Dynamics Constellation, GDC, and the science questions for this are listed here. Pretty much the idea is to look at the ionosphere, thermosphere, and understand the energy and momentum that's flowing from above, from the magnetosphere, generated by the solar wind, and understand also the energy and momentum that's flowing from below, from the lower atmosphere, and to understand how these two sources of energy control, shape, the ionosphere, thermosphere. And to do that, what's proposed is to fly 6 satellites in an orbit, as you see up here, to do this. And this would be unprecedented in the kind of temporal and longitudinal type resolution that we would have. It would probably be about 6 times better than what we have right now. The reality is that this is what we really want. This is really what we want, something like this in some way. And this is 120 satellites. And you sit back and you say, is this at all possible? What if we went up with 10 satellites on each of the next 10 high-latitude launches, and were able to put this up over a year or two, and probably for maybe the same kind of cost as what we were looking at for the previous constellation. So I point out also that there are other ways to fold out constellations instead of going up, say, on 10 different launches and dropping off the satellites. This is a 1-year fold out. This is a 3-month skip after the initial deployment here. And the idea is to deploy satellites at 4 or 5 different altitudes and just let the differential drift of the orbits spread out the constellation. So this is 90 satellites that spread out over the course of a year. that could be achieved with a single kind of launch. Of course, proposed by Miguel Larson as part of his high-def proposal a few years back. Okay, so can CubeSats contribute? And I really kind of come down and say there's really four things that we need to really look at. The first is, do we have miniature space science sensors? The next is, do we really have CubeSats that are capable enough, that have attitude determination and control systems that we would need for the kinds of sensors we'd like to fly? Do we have the navigation and control capability, propulsive capability that we need for CubeSats, or will it be available in the near future? And can we get the data off them so that we can do useful kinds of science? So this is a slide that's going to get me in trouble because there are a lot of people that are working on all of these issues, and I couldn't highlight everything. The slide's already busy and messy as it is. But I will point out that yes, we do have electric fields and magnetometers and Langmuir probes and particle detectors and neutral particle detectors and GPS and imaging kinds of instruments that are all being developed. People are working on broadly throughout the community, a lot of very bright minds working on this. And it looks like they can actually do it. They can make very small instruments that could be used to do reasonable space science studies. Of particular interest to me are the thermospheric sensors. You know, can you really build sensors for the thermosphere and fit them in CubeSat or containerized deployment type systems? And in particular, here's a mass spectrometer that's been tested, a time-of-flight mass spectrometer that's about 3/4 of a liter CubeSat sized here, and it's showing unit mass resolution. Here is a temperature imager, looking out at the limb, looking at oxygen temperatures. We got 9 different slits across here, and then we image an altitude. Once again, a CubeSat-sized optical instrument for looking at thermospheric temperatures. Here's a Fabry-Perot. There are posters on these, this one today actually, down in the poster session. It's a Fabry-Perot wind meter, and it's been built up and brass bored and tested, and they're showing 10 meter per second kinds of winds that could be measured from this kind of a small instrument that you could fly on a CubeSat. So now let's talk about pointing. There are a number of companies that are creating star cameras and momentum wheel systems. I could probably put up 3 or 4 slides like this, but I'd like to just point out this one right here from this particular company called Blue Canyon Technology. The containerized satellite deployment possibility, opportunity, the fact that you can actually build something and get people get it in space has meant that people like this, with lots of experience, essentially the ball kinds of expertise, are coming to this community and providing us these kinds of capabilities. If we look ahead, a program that I've been involved with is DICE, 2 CubeSats, which are up flying right now. We teamed with L3 Communications, and they helped us build a radio that has a 20 megabit capability. And on DICE, we've demonstrated a 3 megabit kind of downlink with this thing. Over the year that this mission has flown, and we have not necessarily worked really hard to try and get all of the data that we possibly could down through this link, you know, several gigabytes from these spacecraft. I would argue that this probably rivals most of the CubeSats that have been flown to date in total as far as data brought down from the spacecraft. Finally, we have technologies like these micro PPTs. This is a 3U CubeSat that we've been studying at Utah State University. The idea is to fly a constellation that is a repeating ground trace type constellation. So in other words, this satellite here will view this region, and this one will come back and view that same region repeating through the same volume of space kind of thing. And these kinds of constellations don't require, you know, more than maybe 100 meter per second kind of delta V. And these types of micro PPT systems produced by companies like Busick out there are available. We can actually build satellites, and actually there's a fair amount of free volume in this one right here, that have the propulsive capability to create constellations that are controlled, and these technologies fit within containerized 3U type CubeSats along with our science instruments. So with that, I would like to conclude and say that really our most significant advances in the next decade are likely to be driven by advances in technology and our ability to observe. And that one of the most promising techniques that we have is this idea of miniaturizing our sensors and our spacecraft so that we can make the multi-point measurements which our data-starved science needs. Thank you.
All right, we have time for one question as the next speaker comes up. Eric? Tom? Yes.
Thank you. Could you comment, I think you guys missed the slide, on the attitude determination control, because a lot of these measurements, the high precision measurements, depend upon that part of the system.
Yes, so this is, there are a number of momentum wheel star camera systems. This particular momentum wheel star camera system is put together by a small company, an SBIR. As far as I understand, the guys at Ball Aerospace were willing to let their expertise go off and spin off a small company. It's been funded, as I said, by the SBIR kinds of funds that are out there, and they have produced essentially they have built and tested a version and are in the process of having something you can go out and buy. And this is the way that the science community really should do this. We really shouldn't try to be satellite experts. We should work on our instruments and buy our subsystems and high reliability subsystems from industry. I don't know, is that enough? Yeah. Okay.
All right, thanks. All right, appreciate it, Charles. Our next speaker is Eric Donovan, and he is going to share with us the next talk entitled "The Next Generation Auroral Imaging from Space." So, Eric.
Hi. Thanks to Jim and Jim for giving me this talk. Again, I'm speaking about next generation auroral imaging from space, and it's a group of us who've been working on instruments and mission plans for, sadly, approaching a decade now, but that's not that unusual. I called out a couple of things in the first couple of slides from the recently published decadal survey, and I just want to point out that I think that as I'm talking about what I'm talking about, I think it's pretty clear that it's highly relevant to all four of the goals, particularly relevant to two of them, and relevant to all four of the goals, high-level goals mentioned in the decadal survey. And one thing I call out in particular is the notional mission Medici, which is in the U.S. decadal survey. Again, I'm in Canada, but we do look to the U.S. plans for validation that what we're looking at is at least relevant on the world stage. And Medici is an imaging mission, and it bears a lot of resemblance to what I will end up with at the end of this talk. I wanted to point out also that beyond the decadal surveys and the roadmaps, the NASA roadmaps and so on, that if you look at GEM and CEDAR and comparable programs around the world, there's sort of a drive, not sort of, there's actually a definite drive towards realizing some advances in what people are calling system-level science. And the idea is not maybe as well formed as it should be, but it's becoming crystal clear that that's a direction that most people, or many people in our international community, really want to go with our science. And that system-level science has to be enabled by different and new kinds of observations. I also do call one thing out of the NASA roadmap, which is from 2009, and that's the dynamic geospace coupling, but there's actually 3 notional missions in the NASA roadmap that also require things like auroral imaging, global auroral imaging. Now, this is a slide that I've shown a number of times, and it does keep evolving, but please forgive me if you've seen this 4 or 5 times, but I think it raises a very important point, and that's why I like to keep making it. And that is, if you look at our field, we really look at how things propagate from the sun to geospace and how things in geospace happen and affect our environment. And if we really have different threads in our field, one of which is solar science, another one which you could call geospace science. And the solar science, by virtue of our view of the sun, is largely imaging. And imaging is about most of what you can do with with the sun, and of course most of the solar missions are organized entirely around imaging and imaging from afar. And that has been tremendously effective in driving forward our understanding of what's going on in the sun. If you look in geospace, I think by virtue of a different view that we have, which is that we can put stuff into the plasma environment. If you look at the list of missions that we have historically, now, and in the future, the vast majority of those are in situ missions. And they're driven by a very different ethos, which is the idea that if you can drill far enough down into the plasma distribution function, you can understand anything. Okay? And I would say that those are very, very radically different views. They're historically driven, but very different things that drive solar science and geospace science. And my argument is we need some imaging, and not just because the imagers don't have much to do. We need some imaging because our science actually fundamentally needs it. Moving on, a couple of reasons why we need this, a couple of things that I think we need to do better in the future than we have done in the past. This is an image WIC image down here on the lower right. Themis All-Sky image mosaic here on the upper left. And what's really been new with the continent scale imaging that we've done with Themis ASI is the ability to track mesoscale motion and dynamics of the aurora, and to relate that basically one-to-one to the motion and dynamics of things that are going on in the magnetosphere. And that's something that we can do on relatively small scales, but that we cannot do on global scales really with any of the existing image data that we have. Another thing that I'm very fond of pointing out is that what underlies the dynamics, the large-scale dynamics of geospace as a whole, is reconnection. Reconnection on the day side and reconnection on the night side. And the competing difference between the night side and the day side reconnection rate is really what powers geospace dynamics. And that's something that I assert we've never measured. We have proxies for the amount of open flux in the polar cap, and that we try to piece that together with things from image or polar, and then we have proxies from the polar cap index and so on. But for something so fundamental and so central to our view of geospace, to what happens in geospace, I assert that it's actually pretty bad that we haven't done this better, longer, and continuously. And what I've got here is from a paper by Mike Henderson, and it's just a keogram in one magnetic local time. And again, we can do this sort of with existing global images. When I say sort of, what I mean is that it's hard to identify really where the open-close boundary is from these images. So we're just saying, well, where it got dark as you move poleward in the image. But that's not clear that that's the open-close boundary. And for something so fundamental, I think we have to be better than, not clear on it. But the idea is that if you could identify the open-close boundary, or really the polar cap boundary, then at a given local time you could identify the dynamics of that boundary. And then if you could do that at all local times, then you could actually track the difference between the day side and night side reconnection rates. You can't really identify either or, but you can do both. And it's really the difference that powers the dynamics in the magnetosphere. It's very fundamental. In order to do this, what we really need to do for global auroral imaging, by the way, is have daylight suppression, which has not really been very successfully done in the past, and also sensitivity. The daylight suppression to allow you to do it at all local times, and the sensitivity to really say that dark means no auroral emissions. If you don't have the sensitivity, you can't say that. Okay, looking as well, something else that we need to do better in the future. This is from a paper by Nikolai Osgaard. Nothing wrong with Nikolai's paper, but we're moving forward in time. Nikolai was using polar UVI and PIXI multi-channel data to look at the global distribution of the energy spectrum of the precipitating electrons. And you can imagine that piecing it together with 2 channels from polar and 2 channels from PIXI, that one, and with poor spatial resolution, one has a hard time, getting a very good picture of this, but Nikolai and his group in Norway did, I think, a fantastic job with what they had. Why we need this? we have to look at energy deposition. We need that in order, for instance, to create global maps of conductivity and how it changes in time. And conductivity is not just a function of the precipitating spectrum. It also is affected by structure, because the structure of the conductivity really has a significant impact on MI coupling. And so this is again an image on the image-wick image on the left, and then Akasofu's old diagram. And we do know, obviously, from all sky images and just from decades of all sky images, that the aurora has large regions that have different types of aurora. And those different types of aurora represent different types of magnetospheric activity and different types of MI coupling. And you can't identify those different types of aurora from existing global images. And so as we move forward, we would need to have images that have the spatial resolution to identify auroral type, have the sensitivity to identify the polar cap boundary, have the daylight suppression to allow us to do that at all magnetic local times, and to have the spatial resolution to allow us to track the dynamics of relevant features on a global scale. Now, it's important because one of the things that happens is if you put people in a room and say, well, let's have a blue sky visioning exercise about this, then people start throwing out numbers like, well, let's go after 1 kilometer spatial resolution and globally, and let's go after 1 second temporal resolution. But there are very, very good reasons, besides cost, why we don't have to go too hog wild on the space and time resolution. And this is a figure from work by Vadim Uritsky, who worked in Calgary for a number of years on our evolving global auroral imaging projects. And the idea here is that you can look at there's a relationship between spatial scale and time duration, and how fast the aurora changes is related to how big the auroral features that you're looking at. If you're looking globally from 1 or 2 locations, there's a limit placed on the spatial resolution that you can get averaged over the whole global aurora, which is really about 20 or 30 kilometers, because there's a height to the emission region. So you can't get 1 kilometer resolution globally from 4 or 5 Earth radii away. You can't do it. So if you're going to get a 20 kilometer spatial resolution, you can look at the time variations that you really need to go after. And if you're going to get 20 or 30 kilometer resolution, you can be very sure that you don't have to image faster than about 10 or 15 seconds. And that actually is quite reasonable with new technology. And so we don't need to push this to some unreasonable level to do something new. In fact, we need to push it to a very reasonable level to do something which I would argue is tremendously new. Craig Unick, who works in my group at Calgary, and Emma Spanswick, who works in my group at Calgary, and also a team of engineers at a company called ComDev in Ontario and Canada, have been working for the last few years, and we've been trying to identify quantitative ways that we can compare the performance of different imagers that have flown and different imagers that we think that we might want to fly in the future. And I think they've come a long way, with this. We can now put about 40 or 50 now different designs, both things that have existed in the past and things people have proposed for the future, and we can place them on various trade space graphs and say, if you want to go after space and time and sensitivity and so on, and you're limited by mass and you're limited by your detector and you're limited by volume, then you can pretty quickly settle on what a reasonable design is. And for the kind of mission that we're talking about, more recently, Craig Unick came up with a 4-mirror, and people who are really in tune with the auroral imaging will know why we need multiple mirrors for this. But we have a 4-mirror design, which is a telescope design, so this is on-axis, not an off-axis design, which is actually, if we were able to build this, it's a nice compact in mass and low, compact in volume and low mass instrument, relatively, that would really allow us to do some interesting things in the future. So what we get with this new technology, this is an image that Emma Spanswick put together. This is an image-wick image on the left. And on the right, what we've done is taken a Themis all-sky image mosaic and created an image of a region about this big here out of real all-sky images with 1 kilometer resolution, but downsampled that to the resolution of polar UVI. Okay? And what happens is you can't see individual auroral arcs and you can't see individual auroral patches with the good auroral imaging that's been done in the past. On the bottom right is the same Themis all-sky image mosaic, but fuzzed to the level of the imager that we're proposing that we fly in the future. And the key thing is that if you can get 25-kilometer resolution, you can see arcs and you can see patches. And there are arguments that you can make also that I think are very compelling, that that's really the lower scale that matters for the magnetospheric dynamics. Also, with this four-mirror design, with this and coatings on the mirrors, in order to do wavelength isolation, Emma's been working with Doug Strickland to look at the photons that are coming off a daylit, air-glowing, and auroral atmosphere, and put it through our filter system. And this is a new step forward, that our signal will be 95 or 96% auroral even in the worst of circumstances. And what that means is that we really, really would be able to see the polar cap boundary, for instance, at all local times. We really would be able to see the cusp aurora, and we wouldn't need to do models to extrapolate what's happening on the day side. Thinking about the missions themselves, you know, I've talked many times about Ravens, but if you want to do continuous long-term imaging, 24/7 imaging, you need more than one platform. That's obvious. If you want to do conjugate auroral imaging, you need more than one platform. And so one imagines either 3 satellites or 2 satellites, depending on how one looks at this. If conjugate, it would be 2 satellites. 24/7 would be 2 satellites in the northern hemisphere. And you can imagine 3 satellites doing conjugate and 24/7. I also am a big fan of recognizing, as the image satellite people did, that auroral imaging is not enough if you want to do system-level dynamics. And I imagine looking at, for instance, soft X-rays or ENA images, which allow you to image what's going on in the magnetosheath, to look at ENA imaging or radio occultation to image what's going on in the central plasma sheet, and using global auroral images to image what's happening in the aurora. And if you had all 3 of those, you would be able to meet the mission requirements of a number of notional missions. This is my second last slide, okay? Sorry.
Second to the last. Go ahead.
Yes, part 1 of the second. No. But just to wrap things up here. So if you wanted to put all this together, you could take one approach, which is to do a monolithic multi-satellite mission. That's a problem. It's hard to come up with $1 billion to do this kind of mission. I've always said this, it doesn't matter. One of the cool things about the aurora, it doesn't matter where your satellite is, it matters what you can see from where your satellite is. And often if you're looking at X-rays, ENA, and auroral imaging, they don't have to be in the same place. Okay? And I've raised this point before, but I think that if you imagine doing this as a series, as in parallel, a number of missions of opportunity with different national agencies funding those missions of opportunity, you could do something tremendously better than what we've done in the past, something that would compete with imaging the Earth the way that people have imaged the sun, imaging geospace the way people have imaged the sun. And you could do this for $300 or $400 million spread over 4 or 5 national agencies. I can't believe I've come to this point in my career, but that's actually not that much money, okay? And so I'll leave this slide up at the end and I'll wrap it up. Thank you.
All right, thank you, Eric. All right, as Adam makes his way up, is there a question? Okay, all right, well, thank you, that's good. All right, so we'll go to our next talk, and it's Adam Szabo, and he is going to share with us about DSCOVR, the high time resolution solar wind measurements. Adam?
Thank you. The purpose of my talk is to convince you that we have still need for extremely high time resolution measurements of the solar wind near Earth. And the upcoming DSCOVR mission is going to make a big step toward accomplishing this purpose. The Deep Space Climate Observatory, DSCOVR, the title is not misspelled, was originally designed as an Earth science mission named Triana to be launched by the Space Shuttle. It was demanifested in the year 2000, long time ago, and put into long-term storage, really long-term, over a decade. However, a short time ago, NOAA has repurposed this same spacecraft to gather real-time solar wind measurements from the Sun-Earth first Lagrange point, or L1, the same location where ACE, wind, and SOHO are currently performing their duties. The spacecraft and its instruments are currently being refurbished, recalibrated at Goddard for a late 2014 launch. And now I can announce on an Air Force-provided SpaceX Falcon 9 rocket. Now, the primary purpose of this mission, of course, is space weather forecasting. To accomplish this, it needs to measure the solar wind bulk properties, that is the magnetic field, and the solar wind proton temperature, density, and velocity on the order of 1 minute cadence in order to provide sort of a 20 to 30 minute forecast time period, thus continuing and maybe slightly improving the current capabilities of the ACE spacecraft. To accomplish this, it has two primary instruments. The first one is a Faraday cup. This was originally built by MIT. Currently, it's refurbished by the same team from MIT, SAO, and Goddard. This instrument, of course, can make solar wind measurements at the 1 minute cadence, but it can do much, much better. In fact, it can do an unprecedented 1 second cadence for the plasma bulk velocities. Bulk properties such as density, velocity, and temperature on a reliable manner. This spacecraft is also this instrument is very resilient. It can withstand high energy particle events. It has a strong heritage, so we think that it will function rather well. It does have an upper limit in energy of 8 kilovolts, corresponds to about 1250 kilometers per second. The second primary instrument is a flux gate magnetometer. This is a standard Goddard flux gate magnetometer, very much like what is flown currently on ACE and WIND. It has the same properties, except we pushed up its cadence, so we will be gathering data at a 50 vectors per second level. Of course, for space weather monitoring, there is no need for all that, but the data will be anyways coming down. The magnetometer sits at the top of a 3.5 meter boom to keep it safely away from the spacecraft-generated magnetic fields. Now, besides the primary instruments, there are a couple of others left holdouts from the original mission. We will have an electrostatic analyzer that will do a nearly three-dimensional distribution function collected almost every second, and it will go up to 2 keV. DSCOVR retained its Earth science instruments, and from some of the earlier GEO talks, as they might be interested, the Earth polychromatic imaging camera is, as the name implies, it's a CCD camera with a 2K by 2K CCD that will observe the whole sunlit side portion of the Earth from L1 continuously, providing really the pictures like what we saw from the original Apollo mission every couple hours. It will do it in a number of different, specifically 10 different wavelengths. Taking differences and ratios of these measurements, one can get such information as the ozone level, the aerosol, cloud heights, or vegetation indices, besides, of course, the pretty pictures. We will also have what is called a NIST Advanced Radiometer. This images the Earth as a single pixel, but in 4 different wavelengths, and it will measure both the Earth radiated and the reflected solar energy back toward the spacecraft, helping us with the energy balance question, again, a couple of previous speakers have mentioned. However, the focus of this talk is not just to showcase the capabilities of DSCOVR, but to remind you that the solar wind is a highly variable medium. This is a typical day from the life of the solar wind. We have density, velocity, temperature, and vector magnetic field over 24 hours as measured by the WIND spacecraft. And the point what I want to draw your attention to is that it is variable on all sorts of scales. There are wiggles here, no matter what scale lengths you are looking at. We tend to look at historically on the larger scale structures, but the more we zoom in, the more structure we find. Specifically, if I take the magnetic field data and do a power spectral density, that is, I just converted to a Fourier transform over it. This is from a day 1997 January. Actually happens to be from inside the magnetic cloud because that's the data I happen to have. This is from the WIND spacecraft again, and I use the 11 vectors per second data for that time period. And notice that, of course, for the low frequencies, we see what is called a Kolmogorov type of fall-off of 1/5 power spectrum. And then we have a turnover at the higher frequencies, which we call the dissipation range, where waves are transferring their energy into the particle temperatures. Very interesting phenomena. However, note that this turnover happens to be actually very near the Doppler cyclotron frequency for the ions, very near 1 Hertz. Now, the best plasma measurements that we have currently do not get anywhere near the 1 Hertz cadence. So all we have currently is magnetic field measurements to try to figure out the mechanism, this tricky mechanism of wave-particle interaction. Once we have DSCOVR up in space with 1 Hertz or better cadence, what we will be regularly getting, we will start to peek into this regime. And of course, we would need next generation measurements that will push this envelope further down. Now, if you are not a particle aficionado of turbulence or wave particle heating, and you are interested more in large-scale structure, here is, for example, a typical interplanetary shock, but I've blown it up in time. Again, this is a measurement from wind. Now, notice that these are 3-second observations, so that's why things look so unusual. If you would plot this on the usual scale, all you would see for the interplanetary shock is that you have a step function. And oftentimes people plot it and think of interplanetary shocks as a basic step function. Now let me overplot on top of it the 11 vector per second data. Exact same time period, exact same shock, except now I'm doing the full-time resolution that is available from wind. And notice that all of a sudden a wealth of new information, substructure emerges. Now we can start to see a foot region increasing, a ramp, overshoot, undershoot, damped oscillation, all sorts of structure, things that we would be completely oblivious of if we didn't have the high-time resolution measurement. Note again, I can do this with the magnetic field today. I cannot do anything like it with the plasma data. However, this is not a simple structure. There are all sorts of wave modes in play there. There are lots of things that we do not understand about the energetics and evolution of interplanetary shock. We need plasma measurements at the same cadence. And to show, to convince you that this is, well, it always looks the same, you always got the same wiggles, here are 2 more examples. This time I picked stereo, just to be different. Stereo has 32 Hertz magnetic field data. Again, 2 ordinary-looking interplanetary shock with magnetic field. And notice how different, for example, the foot regions look like. Some of them has significant wave activity beforehand. Other has much bigger overshoot and undershoot. Each interplanetary shock is different from one to the next. We would need the underlying plasma measurements. So, in summary, yes, DSCOVR is going to make all the space weather requirements, it will fulfill it, it will provide the real-time data, but in addition, it's going to make a significant step forward for science, providing higher cadence plasma and magnetic field data together. However, it's not going to be the final solution for all these questions. We have great need to make another order of magnitude faster measurements that we started to work on, for example, for instruments on solar probe. It is possible to get down to the 10 Hertz level cadences with fields and particle measurements, and I think that will be our next important step in near-Earth solar wind physics. Thank you.
All right, we have time for several questions. Yes, right here, and then we'll go over there. Danielle?
It has an upper limit of 8. It has an upper limit of 8 kilovolts that corresponds to about 1,250 kilometers per second. 1,250. Well, the electrons, yes, at 2 keV, you can go up to thousands and thousands, but that's they have different problems associated with it.
Okay.
With cluster, you have 67 Hertz.
Yes.
But it hits a noise floor quite quickly in the solar wind. Will this have a lower sensitivity, higher sensitivity, so it doesn't hit the noise floor?
Yes, we worked very. I assume you refer to the magnetometer, not the plasma measurements. Yes, the Faraday cups are known to have the sort of level off at around 10 hertz or so. So we worked very hard to clean that up and try to see if we can push that boundary down. To be precise, if I wanted to go to the 100 hertz type of level, I would really want to use a search coil.
Will this happen in search coil?
No. No, so we are pushing the boundary of what a flux gate magnetometer can do.
All right. Thank you, Adam. All right. We now have our next speaker who is also going to continue this theme on a space weather mission. However, looking from a very different perspective with very different instrumentation. So Russ Howard is going to speak to us about a space weather mission to the Earth's L5 Lagrange point.
Thank you. I'm going to talk about a mission to the L5 point. This is the result of this is derived from a white paper that was submitted to the decadal survey, and so hence the large number of co-authors. But I've modified it a little bit, and the errors of the modifications, of course, are due to me. The idea of this mission is twofold. One is to do good science in CME and CIR, coronal mass ejectioning and covariating interaction regions, helioseismology, as well as the acceleration of energetic particles, but also to do monitoring of the solar wind for space situational awareness purposes. The idea being that we can track the properties of structures that will affect the solar wind and Earth for much of the distance from the Sun to Earth. In the decadal survey, there are a number of references to this mission, and I draw your attention to the last line there, that the idea is that it's very important to monitor the variable solar heliospheric photon, particle, and magnetic field inputs with satellites both at L1 and at L5. And then it goes on for a number of other strategic recommendations as well that I don't list. But from table 7.1 of the survey, it shows the L5 should have a coronagraph, an X-ray, UV, and magnetic field imagers, a solar irradiance monitor, as well as heliospheric imagers and in situ instruments measuring the solar wind parameters of field, temperature, velocity, and composition. The reason that this has become important now, I think, is that the stereo mission, which was launched in 2006, has really demonstrated that such a position in the heliosphere as L5 or L4 would be extremely useful for tracking CMEs, in particular, all the way from the Sun to Earth, and that there are no future right now. There are no plans for a future L5 mission. So, what is L5? Where is it? Here is a map of the two-body potential gravitational potential field, and in the yellow center is the Sun, and off to the right you can see a picture of the Earth. I guess I can show that. Here's Earth. L1 is a very common point, and L2 and L3 are metastable points that need station keeping. L4 and L5 are located at about 60 degrees from the Sun-Earth line from Earth, and they are mildly gravitationally attractive, and so it becomes quite a nice place to put a mission. So why L5? One of the interesting things is that you can, with a helioseismology instrument, you can measure the evolution of the tachocline, the lowest surface a low surface where the magnetic field is sort of forming that then works its way up to the surface that we see. You can see the origins and evolution of earthbound wind. You can look at the particle acceleration at the heart of the coronal eruption, and you can do long-term CME studies, stereo studies of CMEs and CIRs. And then look, of course, continue to look at the physical properties of the corona before, during an eruption. I'll skip over these. I'm probably going to run out of time. So one of the problems, one of the advantages of helioseismology is that with two viewpoints, you can then measure this tachocline, the longitudinal variation of the field at this layer, and with a varying longitudinal separation of the spacecraft from Earth, you'll get quite a very nice probing of this layer. Again, we've had a lot of measurements, of course, a lot of observation, many years, but we still don't understand the sources and the processes of the solar wind. And I think this mission is essential for helping to resolve, or at least address, some of these questions. One of the instruments that we would like to put on is a limb spectrometer to do limb spectroscopy. We heard that imaging is important. It is, but it's not the only type of measurements that we do remotely from 1AU. We do measure the spectroscopy of the solar disk and solar corona. And with that, you can really start to probe some fundamental properties of the corona. You'll be able to very nicely resolve some of the earthbound solar wind properties, such as speed and temperature and density. It's the question of where do energetic particles originate? Are they originating from the flare, or are they originating from shock accelerated electrons from the CME? That is still a hotly debated topic, and perhaps it's from both. But which is which? And by doing stereo imaging, we think we can resolve those questions. An interesting thing, of course, is the use of hard X-ray imaging, which the Berkeley group has done, and which we will have on the Solar Orbiter mission. So, from terms of space weather, why L5? The CME is, as everyone knows, the major driver to major geomagnetic storms. And the problem is that you really can't see those storms from L1 very well. You can see the onset of them, or that is not the storm, but the CME. And so this would provide you a very good up to 1 to 4 day warning of the initiation of an event. The question often is it a direct impact, or is it not? Is it something that we will get a glancing blow here at Earth? And by having stereo observations from L5 and then from Earthbound, you can really make some very good assessments of that. This is a plot of the duration, the amount of time from the onset to its arrival at Earth. One of the properties of the scattering of the physical measurement of CMEs from in the coronagraph is the so-called Thomson surface, which is, this is a cartoon, an Apple a cartoon of the intensity of the scattering properties, the scattering efficiency of the process. And it turns out that the L5 is a perfect site for the continual observation of CMEs to Earth. And so we like to think of this as the sort of the Nimbus program for space weather that Nimbus provides for terrestrial weather. So the arrival prediction is currently done just by a parametric empirical formula of the transit time versus the initial CME speed. CMEs all slow down in their transport from Sun to Earth. And so from a study that we did many years ago from using the German Helios spacecraft and the Air Force Space Test Program P-78, we were able to get this empirical curve of how many hours it took from the onset to transit to 1 AU based on the CME speed. The problem is that the CMEs, of course, observations are projected onto the sky plane, so the speeds can be underestimated by quite a bit. So there's this empirical relationship. Another possibility is to look at the expansion speed of the CME in the plane of the sky, and that's been done with these various empirical factors. Another possibility is to fit the height time curve using method of Chen and Kunkel to long-term, to heliospheric imaging type of observations, and you get then the direction of the propagation as well as the magnetic field. The performance of these techniques is on the order of 12 hours or so. So is it feasible? So here's that same plot that I showed before, and what you would do is do a drift from Earth to L5 at about 38 degrees per year, and then orbit around L5 with a very long, very gradual range of longitudes. That's the minimum energy configuration. You're then trapped in the L5 gravitational well, and with the minimum amount of energy necessary. So here's the strawman payload, and it is a combination of proven instruments as well as some new ones, perhaps. So I believe it's the optimum mission. I think the time is now to start planning for it. It leverages science from that we've been learning very, very, very rapidly from SOHO, Stereo, SDO, and Hinode. And really the next step is now to convene an STT to further define the mission. With that, I think I'll stop.
Thank you. All right, as Tony makes his way forward, is there, yes, a question here in front?
First, what would happen if you also had an L4 mission too? Then you would have all the sort of the advantages of stereo.
Yeah. Yeah, I think it's just a question of cost. We've done a sort of an estimate of this, and the cost is on the order of $500 million, something 500 to 600 million. And a possibility is to do this mission instead of with a single spacecraft, to do it with CubeSat. Oh, sorry. So we had estimated the cost of this mission at about 5 to 600 million, maybe it was 4, depending upon how many instruments were selected into it. And so I think the cost is very dependent on the specific payload configuration. recently, we've been thinking about, could this be done with a constellation of CubeSats? The answer is probably yes, and that's very intriguing, where each CubeSat, each part of each CubeSat module would be dedicated to a particular kind of observation, so that, for example, the magnetic field in situ could be located separately from an imaging instrument array, which might have motors and so on. So that's really intriguing. And the cost of that then comes way down. And so yes, you could do it L4 as well. I think in terms of a single instrument or a single platform that images CMEs all the way, L5 is the better mission. But for looking at, for example, underneath a flare event, L4 would be a better spot.
All right. Just one quick question. You mentioned some of the instruments are stereo light, some are new. What is the single most technological barrier that you see is needed for a mission like this? Just one. What's the biggest technology besides cost?
I think cost. I think funding is the biggest problem.
Okay, but you think everything else?
I think everything else. I think there's very little.
Okay.
Very little improvement unless you go to CubeSats.
Okay.
And CubeSats is so intriguing that I think we have to go there.
All right. Okay. Thank you.
Mm-hmm.
Our last talk today is by Tony Case, and he's going to share with us a talk entitled "Predicting the Inner Heliospheric Solar Wind Conditions in Advance of Solar Pro Plus."
Great.
Use this.
Okay, thank you. Thanks very much. Thanks for having me speak in this session. So I'm going to speak about the Solar Probe Plus spacecraft and a little bit of work we've been doing in predicting the plasma conditions in the inner heliosphere in advance of the mission. I'd like to acknowledge my co-authors, as shown on the slide, as well as the entire SWEEP team and Predictive Sciences for a model that we used in some of this work. This is the Solar Probe Plus spacecraft. The plus in the name implies that there was something beforehand that was not called Plus. That was Solar Probe, and there was a few different iterations of that spacecraft and that mission profile that went to various heliocentric distances. This iteration of the mission goes into 9.5 solar radii at its closest perihelion, and it reaches that point by spiraling inward via multiple Venus gravity assists, which occur over about half of a solar cycle, allowing us to observe a wide range of solar conditions. The payload has plasma fields and energetic particle instruments, as well as a white light imager. And if you look at the image of the spacecraft shown on the screen there, you can see that the top half is dominated predominantly by a large thermal protective system, or a heat shield, as well as a structure, a support structure which holds the bulk of the instrument payload back on the spacecraft bus well away from the thermal protection system, allowing most of the instruments to operate in a relatively benign environment, with a couple exceptions, which are the electric field antennas and the Faraday cup, which I'll talk a little bit more about in a few slides. The background image here is a picture of the solar corona during a total solar eclipse. And you can see that there's an immense amount of structure in the corona. And even out to 9.5 solar radii, which is where Solar Probe will make its closest approach, you can see there's a lot of structure that the spacecraft will fly through. It was known early on that the corona is at a much hotter temperature than we would expect, and it's still an active area of research where how exactly the energy is transferred from the photosphere up into the corona. So that's one of the primary questions that Solar Probe is designed to address. In addition to that, we'll be looking at solar wind acceleration and the continued heating of solar wind as it makes its way out into the heliosphere. And we're also going to map source regions of the solar wind that we're observing in a way that we can't do at 1AU because of the mixing of solar wind as it makes its way out into the heliosphere. Here's a single example of one model prediction that is going to be benefiting from
observations that Solar Probe Plus will be able to make. So this is a plot of the RMS velocity fluctuations observed in the solar wind as a function of the distance from the solar surface. So on the left-hand side here is the solar surface, 1 AU out here, and is that chopped off over there? I can't tell. Okay, anyway, all right, so 1 AU is on the right-hand side of the screen there. Anyway, so there's observations shown on this plot in color. There's near-sun observations on the left-hand side here that were made remotely, and there's in-situ observations over on the right-hand side made by Helios and Ulysses out to 1 AU. And there's a few models shown on here by Steve Cranmer that show a couple different predictions of what the velocity fluctuation distribution might look like throughout the heliosphere. And one of the predictions, which includes a damping term, shows that there's a key region of the heliosphere in which this damping takes place, which is between about 10 and 100 solar radii. And the observations made by Solar Probe Plus will be key in assessing the validity of models such as this. The plasma instruments on Solar Probe Plus are shown here. There's 4 separate sensor heads. Working from top to bottom here, there's a Faraday cup that actually pokes around the thermal protection system, allowing it to view the solar wind when the solar wind is flowing radially. And that cup is designed to measure both ions and electrons. There are 2 electrostatic analyzers on the RAM side of the spacecraft, one to measure ions and one to measure electrons. And there is also an electron analyzer on the anti-RAM side of the spacecraft. So with the combination of the 3 electron sensors, we have a good view of the entire sky, allowing us to, for example, be able to measure the electron straw at any time, regardless of the magnetic field orientation. And we also have a view of the core of the proton and the alpha distribution because of the 2 ion sensors. We can view that distribution over the entire orbit. Here's what the Faraday cup looks like in its current design. Thanks to Adam for the intro to Faraday cups earlier and a look at a previous Faraday cup. So this is actually very similar to that Faraday cup that he showed for the DSCOVR mission. The biggest difference here is that you can see there's a thermal protection shield at the front of the Faraday cup, but there's a hole in that shield allowing ions to flow directly into the cup. There's some advances that we needed to make in materials and in techniques that allow us to produce a cup that can actually sit out in the direct sunlight and still function with the performance required to meet our objectives. I'll just highlight one difference in this Faraday cup compared to previous cups, and that is the method by which we're producing the grids to go into the cup. Here's a close-up view of one of the grids that we're using in some of the Faraday cup prototypes. And instead of, as in previous cups, using a tungsten wire that we weave into a mesh, this is now a monolithic piece of metal that we etch into a grid design, which allows us to retain the high transparency needed, but gives us the strength and allows us to operate in this extreme thermal environment. So a little bit about some predictions we've been making about the inner heliospheric plasma conditions that allow us to develop some of the design requirements necessary to design the Faraday cup. I'll start off with a simple model that we use so we can quickly extrapolate what the conditions at any point in the Solar Probe Plus orbit might be. We start out with 1 AU observations. So shown here are distributions from the WIND spacecraft. You can see the as expected, as we're used to, 1 AU anti-correlations between density and speed and correlation between temperature and speed. And we use these distributions and then map them inwards via power law fits to Helios data. So here you can see 3 different fits that we've made to Helios data showing velocity, density, and temperature from top to bottom as a function of the radial distance from the sun, from the surface out to 1 AU. And we essentially take the 1 AU observations and scale them inwards to 9.5 solar radii. So for example, we've used this to derive the minimum and maximum current fluxes that we'll need to observe with the Faraday cup to set, for example, the size of the limiting aperture that allows us to make these measurements with the noise threshold that we have and at the cadence that we desire. We can look at a more sophisticated model that might allow us to better get a view of the global structure that Solar Probe Plus is going to fly through. So this shows some results from the mass model, an MHD model of the heliosphere. And the color map shows the magnetic field strength, with red being one polarity and blue being the other. And overlaid on that is a dashed line orbit of Solar Probe Plus with a plus indicating Solar Probe Plus. And this will be a movie, and you'll see the observed conditions at Solar Probe Plus fill in on these time series. In particular, also of interest is this plot at the bottom that shows the alphanic Mach number versus the sonic Mach number as the spacecraft goes through this orbit. So an interesting time period during the orbit is right there. As you can see, when the spacecraft reaches near the perihelion, the plasma conditions go subalphanic for a couple days. And this is one of the primary interesting features of the orbit that drives the Solar Probe Plus objectives. Also of note are these blue bars here that show co-rotation time periods, which are an interesting time during the orbit in which the spacecraft's orbital velocity matches that of the rotational speed of the sun. So in essence, the spacecraft is hanging over one place on the sun, allowing us to observe the solar wind convect past us that's coming from a single source on the surface of the sun. So in summary, Solar Probe Plus is going to fly to within 9.5 solar radii of the sun's center, and it's going to give us a unique view and an opportunity to test models and theoretical predictions in a region of the heliosphere where those models have been making very specific predictions. Some advances in technology have allowed us to place a Faraday cup in a very difficult position, sticking around the heat shield, and into a thermal environment that is very challenging. But because of that, we've designed a suite that it will be able to provide us solar wind measurements throughout the entire orbit of Solar Probe Plus, and in both ions and electrons. Some next steps here, we want to, and we hope the community can continue creating theoretical calculations and numerical simulations that make predictions and identify observations that can be made by Solar Probe Plus that will allow us to distinguish between different models of, for example, coronal heating. We also will need to develop some new analysis techniques, since some of the assumptions we use in analysis of solar wind data at 1 AU will no longer be valid in these new regimes of the solar wind as we make our way into 9.5 solar radii. So it's a very exciting mission, and I'm looking forward to all of the exciting science that we're going to be able to make with these new observations. Thank you.
Thank you, Tony. A few questions? Yes.
What sort of ion mass range? Well, we're primarily sensitive to protons and alphas with the Faraday cup.
Over here?
8 kilovolts. So again, corresponding to the 1,250 kilometer a second protons that Adam was talking about earlier with the DSCOVR Faraday cup.
Yes.
Sorry, can you say that again? The predictions right now are that the hottest part of an exposed grid are going to be around 1,000 Celsius. So there are materials that work for this. So.
Right. Any other questions? All right. I want to thank all the speakers for this session. And this last talk was very fitting that we finished that way in the sense that we're talking about innovative technologies to address our future when budgets are likely to be flat, which is the new growth. And so as we go forward, it's going to pay off to be creative and innovative in terms of how we address the science problems we have. So thank you very much.